My name is Daniel Montesinos Capacete, and here we are in the first day of this introductory course to quantum mechanics and computation. So basically, at first we are going to talk a little about the overview of the program. Before saying all that, I want to say that if anyone wants to stop me at any moment in the lecture, feel free to ask any question or anything. I mean, this should be I'm going to give the output, but I also want to give some input from the students, right? So feel free to ask me anything. All right. So basically, the program objective is to give a beginning of learning introduction to the basics of quantum computing. We will learn some basic mathematical tools, revise the principles of quantum mechanics in order to properly understand some basics of quantum computing. And my idea is to leverage between precise mathematical definitions and also try to give an intuitive approach to make it easier, right? So we will not cover like very difficult or abstract mathematical stuff, like yeah, for example, deep functional analysis or distribution theory, and we will not really give proof or for theorems or something, some result that might be quite more difficult to prove, right? So a little about me that for you to know my background, right? So I a few months ago I finished my bachelor's degree in Granada, University of Granada, Spain. While doing that in my last year, I did a collaboration grant that was related to preparing a practical session for a master that was in quantum technologies. The practical session was about working with a trap ion in order to generate a quantum bit, right? And apart from that, I'm right now uh, pursuing an online internship in machine learning. And apart from that, in September, I will be starting a master's degree. So that's basically my background. And also the motivation of this lecture, apart from that, I like teaching, right, and spreading knowledge and all that stuff. I also participating this summer in the Womanium Quantum Program. Womanium is an organization that basically it's try to encourage and empower young girls and women in different science aspects of science, technology, this kind of things. So I'm in this quantum momentum program. There is a module that in order to complete the module, you have to teach quantum computing. Like to encourage people to know about quantum computing. So that's basically where I started to think about these lectures. So the program overview that you can also see in the Discord server, right, in the info lecture channel, is going to be this one. At first, we're going to be discussing a few mathematical tools, basically understand the complex numbers, and also a little introduction to Hilbert spaces. After that, we will deal with a very quick, easy introduction to the fundamentals of quantum mechanics, following by some introduction to quantum computing. And after that, I decided to just give one final lecture about a little of this, how to implement, right, a qubit that will be the quantum bit, right, using a trap ion. That was basically my um, collaboration grant that I told you before, right? And that's going to be basically everything. So uh, is there an, if there aren't any questions, let's just go straight into the first day, right? It's going to be introduction to complex numbers. So yes, exactly. So this will be the index we are going to cover today. at the beginning we're going to be the revise basic text number and try to justify the why we need complex numbers. After that, we will define complex numbers, see how to work with them. Also, try to see different ways to write the very same complex number. At the end, some properties and also a little some reference in order for you to maybe look at those things more deeply. So, basic type of numbers, right? Um we are used to work with these numbers in the sense that in our life, in the traditional mathematical problem that we face in high school, these are the types of numbers that we face, and this is the structure of the numbers. I don't know if you may have seen this before, but basically it starts with natural numbers, right? And natural numbers. Basically, some people don't like to add the zero here, but I have added. I mean, it's not important. Some mathematical people they know natural numbers don't have zero or whatever, but that's not much important for our purpose. So basically, we start with natural numbers. Uh, After that, we have integers numbers, right? So, and these letters here is like a mathematical symbol to represent this set of type of numbers, right? So we have here the integer, the set of integers numbers. That is just every integer number, including the negative ones, right? All right. Going, I mean, like going into the rational numbers, we have a bigger group, right? Because a rational number is just a number that can be written in this form, right? I mean, I don't know if everyone is familiar with mathematical notation, but in here I'm just saying that rational numbers, right, is the set of points that can be written in this form, where P and Q are integer numbers, right? Here we have few samples of rational numbers. So with that, we have like a lot of different numbers, but it's still not every number we can find, because there are some numbers that you cannot really write in this form because they have in infinite amount of decimals, right? So there are here a few samples of these numbers. They are called irrational numbers. There is no specific definition like this one. I mean, we will say like uh, irrational numbers are all the numbers that are not rational numbers, right? So, for example, it's very, I mean, and maybe it might be sound a little abstract, but for example, if you have a triangle, right? Imagine this one is the size is not very right. Imagine this is 1 meter long, and this is 1 meter long also. So basically, using Pythagoras theory, this will be the length of the one will be a square of 2, right? And this is an irrational number. So I mean they are like they are there, all right, but they are a little strange in the sense that you cannot write them in this way. So basically, when you take rational numbers, and that means that you are also taking integers number and natural numbers, which irrational numbers, you have the set of all real numbers, all right? I mean, this is quite basic, but I think it's good to explain things step by step, right? So that's it. I guess is if no one says anything, I will think that everything is fine. So I will move on to the next one. So let's take a really easy example. I mean, is this everything we need? Like all this number is really everything we need in order to work and solve every problem we may face. So for example, let's take this high school problem. So we have here a quadratic equation, right? And we know that the solution for this equation is has this form. Fine. So for example, if we have this concrete case, we use a formula if I haven't done anything wrong. So this will be the result, right? You have to choose solution since you have a quadratic formula, and that should be fine. All right. But what happened is, for example, we have this equation here that is like mostly the same equation, but we just change the sign, right? When we change this sign here, basically we are just, because it will be C, right? So we are changing the sign here, fine. So now we have a -8, right? So basically at the end we got the root of a negative, the square root of a negative number. Um, we know, or I don't know in high school, what would your teacher, what they have told you about this. Normally, the more precise answer will be this one, all right? That there's no real number solution for x in this situation, right? I mean, that will be the solution. And in that case, you say, okay, there is no solution for x in the real domain, right? But if we want to go maybe outside of the real domain, and that, I mean, at this point, we don't really know what outside of the real numbers set, since we haven't really described any other type of number, right? But we might be interested in doing that, since this problem right over here, that is quite easy. No, in the sense that, I mean, it's the very same equation, but just changing an aside. How can we solve this, right? I mean, there must be a way to solve this equation. So we do the following trick, right? So -7 will be the very same as -1 times 7, and this will be the same as this equation. I mean, a square root of -1 times a square root of 7. Yeah, at this point, here is a trick. All right, we call this quantity, we call I, right? So this is the trick, basically. So at this point, the solution to our equation will be this one, right? But I mean, this is not really, this is not a real number, right? I mean, because in here we have the I. So this must be another type of number that is outside of the real number set, right? And I guess that if this is the very first time that you are seeing this, you might be a little, this might seem a little crazy, in the sense that, like Jackie Chan here, in the sense that, because it seems that we haven't done anything really. I mean, in the sense that we have just struck the -1 and call it I, and that is like doing anything. All right, but um, anyway, um, this is the main idea that comes, or the a very intuitive and easy approach to introduce complex numbers, because I mean there could be a lot of more mathematical details and explanation, but basically complex numbers are just another type of number that can be written in this form. Now I will define in a better way, and they appear sometimes when we solve problems, and they are extremely useful, right? I mean, in here this is like a very toy example, right? But they are extremely useful, in the sense that there is I mean, there is a whole mathematical branch, is complex analysis, and is extremely useful and amazing. All right, so what is exactly a complex number? So this is the set, this is the letter we use for the set of complex numbers, right? So a complex number is any number, right, that can be written in this way, where a and b are real numbers, and a is the square root of -1. And normally it's common, right? It makes sense to call I the imaginary unit, in the sense that, I mean, this is quite it's a traditional name, because it's because at first when they were developing this, right, it's it was called like these are also called imaginary numbers, right? So This is called the imaginary unit. Yeah. Basically, so if we have a complex number called uh, yeah, zeta, um, we can have this is called the real part of zeta, right? This is the real part. This will be uh, this will be here the imaginary part, right? And I mean they are both complex, real numbers, right? In the sense that since we have here the definition, every real number that we have discussed before. So that's basically the definition I would give for complex numbers. Well, so for example, we can compare complex numbers to a point in the two-dimensional plane, right? Where here the axis, right? This axis, this horizontal axis, is going to be the real part of the number, and the vertical axis is going to be the imaginary part of the complex number, right? So, for example, if we have this point here, this will correspond to these complex numbers in the sense that, all right, your imaginary part will be 4, right? So you have here 4, and your no, right, I'm your real part, right? Sorry for that. This will be your real part, and you will put the point here, and also you have your imaginary part over here. So this will be this point. You have this point in the to the plane. You can also go to maybe 4 and 5 this point, right? So that's another example is basically saying you have -2 uh, as the real part, and also -4 as the imaginary part. A curiosity here, well, maybe it's quite maybe easy to see or not, but this I mean horizontal line, that is the real part of your number, is basically every point in this axis is going to be a real number. I mean, this is the axis of real numbers, because every point in this line is going to be a real number, right? Because it has imaginary part equals to 0, right? Just a curiosity. Also, since it's graphically easy to see that you can define the module of a complex number, that is basically the same of the as the module of a vector, right? Straight line, please. Right. So this will be module of this complex number, right? And it's just, I mean, this apply Pythagoras theorem, right? I think there is not much problem in that. Like, yeah. So basically, you have this example of which these two numbers. You have to the root of the sum of the squares of the real part and the imaginary part, right? Very well. So here just few basics and very fundamental operations with complex numbers. So first we define the complex conjugate, right? So if we have here these complex numbers, the complex conjugate will be denoted in this by this notation, in the sense that just adding this little start of asterisk here. This denote this is the complex conjugate of this complex number, and the complex conjugate is just basically changing the sign to the imaginary part, right? So that that's I think is quite easy to see, right? So it's just changing the sign, right? So for addition and subtraction of complex numbers, is just, I mean, I guess it might be strange at first, but they work exactly as usual, in the sense that you have your first complex number here and your second complex number here. You just go, okay, a1 plus or minus, right? A2, so you have a1 plus minus a2, and since you have the I here, like you can just sum or subtract the B1 and B2 to the A part, right? I mean, I believe this is must be quite straightforward, so no, don't want to lose much time in this. Also, it is quite interesting to see or just to remark the powers of I, since I is this unary imaginary unit is defined by the square root of -1. So we have like the e square is -1, right, for sure. Also, if you do the power of I to the 3 will be minus I, right? Just take -1 times I, all right? Also, the imaginary unit to the power of 4 will be just minus I times I, right? That will give you minus I squared, and that will be -1 squared. That will be 1. And when this at the when we have I to the power of 5, we have we start again, right? The loop because we have again our imaginary unit, right? So one important, really important thing about complex numbers is that you can have numbers, right? Then when you uh, calculate the square of the number, they can be negative, right? And that is something that never happens in the real domain, and we are used to seeing that if we have a square number, I mean this this we are used to seeing in this term, like if we have a number uh, square, it will be always 0. But in this case, this is not true because since we are adding this imaginary unit, it can happen that this this might be true, right? So be careful with that, right? So more basic operations. Basically, if we want to multiply complex numbers, is again the same as usual, right? But yeah, I take here the sample. I mean, I just go A1 times A2. Now A1 times B2 times the imaginary unit, right? Uh, B1 times A times A2, right? Here we have it. And also B1 times I times B2 times I, right? So you have here, so the funny thing is you have here the I squared here. So this will be -1, right? So this -1 is what you have. Oh, I forgot to add here another. I mean, I added the colors, right? I mean, this should be like in orange, right? Mm. Well, more or less. Right, so this I square is -1. So that's why you have here the B1, B2 term, also the A1, A2, and this will be the complex part, right? So that's multiplication, quite just multiplying that like usual. Also, in order to divide by a complex number, it gets, I would say, a little trickier, but it still be really easy. So imagine you have the division of two complex numbers, whatever complex number you want. So if you want to make this operation, right, you have first to multiply by the complex conjugate. I mean, if we call this, let's say, yeah, theta, to, right. So you are here just multiplying by the complex conjugate, right? I mean, this is one, right? Because we are multiplying and dividing by the very same. So this is equal to 1. So we are allowed to do this. I mean, when you are doing calculations, it's quite usual to use this mathematical trick, just multiply by 1. But in this case, we are going to write 1 just by in this way, right? So when you do that, you get this, right? So basically, let's go here. When you do the multiplication, in this case, when you have your numbers, it will be this, this, this one, this will be this one. So in here you have this is a property. that I will highlight later. But basically, you have here the module of your complex number, and in here you have the multiplication, just taking care of this sign. It's not exactly this, right? So, and that's basically the division. I mean, I hope if there is any no question, I hope everything is easy. Everyone is understanding everything properly. But feel free to ask me any question I have said before. Very well. So now we can um, write our complex number using different coordinate system. We might say, right? So just another way to writing the same, right? Uh, this is going to be useful for many things. So that's basically the reason to do this. But if we have our complex number, right? As any complex number, I have put in this part of the plane just for to be more intuitive and easy. But if it can be any complex number, right? We can define this angle. This orange line will be the module of your complex number. So using basic trigonometry, like the very definition of the sine and cosine of an angle, we can see that the A, I mean, if we have theta, yeah, well, A minus AB, right? I mean, this will be B, right? And this would be A. So I believe it's quite easy to see that these equations are right, just using basic trigonometry. So, I mean, using this general form that we have already seen a few times, is quite straightforward to write your complex number in this form, right? I believe this is okay. So this will be useful for the next form we will see. But before saying that, I just thought it would be interested to highlight that there exists, well, what is called the Moivre formula or theorem, right? That is, yeah, I'm not going to prove the result. I mean, you can search on Wikipedia or whatever, or if you are very, very much interested, since we are not really going to use it in this course, I thought it would be unnecessary to prove it. But it's just a formula for computing the the power of a complex number when this number it must be an integer, right? It cannot be rational number or other stuff. All right, so that's the trigonometric form, right? So now let's move to something that might be a little more complicated to understand or not. But I mean, this one I want to give a little proof. So that's why I have in here this mathematical help, right? But let's try to forget about this right now. I mean, all right, I mean, not don't look at this horrible. I mean, this is uh, complementary, right? This is not really the main purpose of this slide, but this I'm going to use this to give a little proof of this step. So no, of this step, right? So basically, we have this identity that you can write this uh, this expression, right? I mean, this is a equality that holds, right? If you compute this, and that's the proof I want to give, I will give now. You can see that this equality holds. So you can write your complex number using the trigonometry form we have seen. I mean, we have just seen. You can write your complex number in this way, and this is called the exponential form, and it's quite the best. I mean, it depends for sure in what you're doing and what you have and what they give you or whatever. But it's quite useful and easy. I mean, normally it's more comfortable to work with this form of the complex number because it's quite it's easier to make computations in this form, right? So in order to uh, understand a little where does this come from, I need to use these these sums over here. I mean, I guess everyone is familiar with. I mean, this is just a sum, right? I mean, for example, if we remember here I'm summing, summing over n. So I go to example with maybe the sum over n since 0 to 5, for example, of of n, right? This will be just 0 plus 1 plus 2 plus 3, right? Plus yeah, oh my god, that's fine, right? I mean, yeah, we are just summing, right? For example, if we have this one, right? You can say uh, this will be 0, right? 0 factorial. Maybe one factorial. Yeah. So, but this will go to infinity. I mean, I don't know if you may have seen this before. These are called Taylor series, right? And it's basically a way to write a function in terms of a series of x. I mean, x to the power of something, right? So you have your x to the power of something here, and this is just a coefficient that might depend of none in the this number here, right? I mean, normally it depends, right? For example, we have the n and we have n factorial here, right? So this is just a specific way of writing some functions, right? So using this, I'm going to, one moment, uh, I'm going to add an slide here. All right. And just adding a slide to do the computations, right? So we are going to begin with this one, right? This is what we have here, right? I mean, I also want to do this proof because what I'm going to do right now, I mean, for proving this, is something that I would say you use sometimes in quantum mechanics to do some calculations too, because in quantum mechanics you have a lot of exponentials. I mean, they are not exactly exponentials of just a number. You have exponentials of operators. That is something I haven't talked yet. But this calculation is going to be useful, I believe. So that's mainly my interest in doing this. It might be a little more complicated, but I hope that it's not going to be so complicated. So let's go. And factorial, and in here I have this, right? I mean, in my case, right, I have x. So my x is basically this. Fine, very well. So now I believe it's going to be the trickiest part, since it's going to infinity, because I'm summing, right, over an infinitive amount of numbers. So if you try to write this as I have written before, let's try to I try to write this in an easy way. This will be 0, 0, to the power of 1 factorial, right? Okay, I think this would be enough and more, right? There is an infinitive amount of terms in your sum, right? But if you see here, right, this would be equal. This one is will be equal to 1, right? Because this is 1, and any to the power of 0 is also 1, right? In here, just because we have I to the 0 equals 1, right? In here, we have I to the 1 equals I, right? I'm not doing any magical trick right now. So here we have I to the square root of minus 1. Here we have uh, minus 1, yeah, right? So this would be minus, yeah, minus a, right? So basically, what we can see here is that if we have e in this way, I mean, this means is the power of I to uh, an even number, we will have minus, uh, look, this is, yeah, because we can see an easy way, right? We can write this in this way. So this will be minus 1, right? I think is good or easy, this one. And also, okay, because we have in the sum, we can see that we have even numbers, right? And how to say? I mean, and not odd number, right? And odd numbers. I wasn't sure how to say odd numbers, right? So if we have this number over here, I mean a to the power of an odd number, uh, what we can do is basically the same, right? We have this and a, and this will be minus n I, right? I mean this is the same as this, so it's minus 1 to the power of n. All right. I mean, I hope this is fine. So what I'm going to do is to, in some way, decompose this sum in two sums. That one is going to be a sum over odd numbers, and the other one is going to be a sum over even numbers. And I mean, the two sums for sure are going to be equal to this one, right? So let's call this a bracket, right? So if I have this, right? Oh, all right. So I'm going to sum over n equals to 0 to infinity, right? But in here, I'm going to do maybe the even numbers, pi, this is 0 to infinity, and now the odd numbers, right? I mean, I guess it might look a little strange in the sense that I'm using the same limit here, but it's the same since, for example, you can check, right? I mean, it would be when n is 0, right? I mean, this will be strictly 0, 0 factorial. This will be 2, 2 factorial, right? So we have, uh, let's use another color. We have this one and this one, right? This one and this one. And if we do this, right? Uh, yeah, we will have, uh, yeah, so basically when it's 0, we will have 1 over here and also 1 over here. And when it's 1, we will have 3. I mean, they are, this number is going to be, well, let's use another color. I have a lot of colors, right? I mean, so I hope you more or less see in an intuitive way. I mean, I understand that this might be a little more difficult. I don't know, but so now that we have done this, is just a straightforward calculation, I would say, in the sense that well, I'm going to use this property. I mean, why did I do this? Because I noticed that if I do this decomposition, I can use these properties, right? And that's the main purpose of doing this kind of decomposition, right? So this one is going to be minus 1 to the power of m. So let's write that. Yeah, minus 1 to the power of m. Very good. And also here we have -1 to the power of n times a, the imaginary unit. Oh, I forgot here this, right? Sorry for that. Uh, Here and also, I mean, here I have applied this, right? And also this. Uh, and just, I mean, I apply the power. I mean, I haven't done anything strange at basic operation, mathematical operation, right? So this imaginary unit doesn't depend of n in the sense that it's not to the power of n or anything strange like that. So it means that I can take out because it's just multiplying the whole sum. I mean, if every term of the sum is multiplied by a, it's like you can take out the a in order to multiply the whole sum uh, times a. So that's I think I'm going to just do this for the sake of finishing quickly. I mean, this is the last thing more or less. So, I mean, we will finish soon. I would say. Very well. So just do exactly this. And now at this point we have what we wanted. And if you don't see that, we go back here. So I think look at this, right? This is basically the what we have uh, do here. This is the, I mean, I can even copy in order for you to see more clearly. Uh, I'm going to erase this. Mm, Very well. Very well. So you can see we have 1 to the power of m and 1 to n factorial to n factorial. Our x has turned into the angle theta, right? Uh, we, and also here we have the same, right? So this all calculation was just to say that this is cosine of theta plus I times sine of theta, right? Right, because we started here, right? Very well. So just is the property we use here. I mean, I could have done this, but I think it was okay to do this in the sense that it's something useful. That I mean, we are not really going to use this anymore. I think. I mean, I'm not sure, but because I haven't really finished to or the PowerPoints, but I'm not sure. But it's quite useful, right? I mean, also try to understand Taylor series is quite essential for almost anything in your physics life. So basically, yes. Uh, so yeah, that's important things. Well, just some curiosity. The Euler's identity, that is just this equation, is like a special case of this. Yeah, yes, I mean, is a special case when you have module one, right? If you have module one, you will have one e, right? So this complex number, if you go to the first form, that happens. I mean, if you go to this way, this is. I mean, I haven't said, but this is usually called the binomial form, right? This is usually called the binomial form. So if you go to that binomial form, you will see that this, I mean, times one, I mean, you got is equal to -1, right? So that's yeah, basically this equation. An easy way to see this, right, is just go to, let's go here, right? So basically, we have in Euler's identity, I say we have theta equal a pi, right? So theta is this angle. So if we have city Wallapine, we will be here, right? I mean, in this part. I don't know, maybe it's not the best color for showing this. Oh my God, no, I don't know how to do one. Right, so we will be in this part. So if we have module one, we will be exactly at this point. I mean, in the -1, right? So that's also maybe why it is quite useful to use the exponential form, because knowing the angle and also the module, you can easily have in your mind, for example, another. Yeah, maybe I should have write this on the PowerPoint, but another to the power of the complex unit, the imaginary unit times pi over 2, right? This is just the imaginary unit, yeah? Because I will erase this, because if you follow the same idea, I mean, uh, like pi over 2 is just 90 degrees, right? So, and if you have module 1, you will be here. And since this is your imaginary part, this means that your complex number is just the imaginary unit, right? I mean, if you, for example, have instead of you have this will mean you have 5i, right? Okay, I hope this is understandable and reasonable. No, okay, okay. So, with all that said, I mean, if there are any question about anything I've said about this calculation, uh, ask me, or just let's go. This is the last slide. See. This is just the last slide. So in here, I just write a few properties that are quite common and sometimes useful. So I mean, the first one are quite toy properties in the sense that if for the complex conjugate, right? I mean, if you have the complex conjugate of the sum of two complex numbers, is equal to the complex conjugate of each one of them. I mean, the sum of the complex conjugate of each one of them. Also, if you multiply two complex numbers, the complex conjugate will be equal uh, to this expression, right? So the complex conjugate of each of the for the multiplication of the complex conjugate of each of one each if each of them, right? um. Oh. All right. Here, there is a. I mean, yeah. All right. So here is another property. I mean, there is a little problem here because I wanted to write another property. I mean, forget about this one. I mean, it's the same as this one, right? So I wanted to write here uh, because this is an expression for calculating the imaginary part out of a general complex number. I mean, if you have this form, it's quite easy, right? Because this will be b, sure, the imaginary part. But if you have your complex number written in this form, it's not so clear what is the imaginary part of your number, right? So this is just sometimes useful to calculate the imaginary part. Right, and also there is also another equation that is basically the same. It's just real of theta 1.5. There is no a here, all right. There is no a here, and flux your complex conjugate. I'm running out of space. But I hope you understand my letters. I mean, yes, the real part of theta is just 1/2 of the sum of theta plus its complex conjugate, right? So I mean, you can, if you use this form at b times a, you can try to check whether this is true or not. I mean, it's quite, I mean, a straightforward calculation, so you can try to exercise a little. Also, this property I told you before. Uh, this guy, if you have any complex number, and you do this calculation, and I mean, you multiply the complex number times its conjugate, its complex conjugate, you can do this calculation by doing the multiplication we have seen before, and you will have the modulus square, right? I mean, this is a square, this square, right? So that's a real useful for quantum mechanics. I mean, it's quite, I mean, basic property, but you use that a lot in a daily basis, since you can, there are a lot of complex number and module of stuff and whatever. So that's a very, yeah, daily basis operation. Also, another curiosity might be that if you do the complex conjugate 2 times to the same number, you will have the very same number. I mean, that's what I mean. You go to the definition of complex conjugate. You will go to a minus a by a b. But if you do again, you will again change the sign, so it will be just the same, right? Fine. Uh, Another project, this might not be so easy to see, but I dare you to try to check this. I mean, it's not complicated. You can just use your trigonometric form. For example, it might be easy, I guess. So, but if you do the complex conjugate of this number, I mean the exponential form, it's just you just need to change this sign, and this is also quite useful to do a straightforward calculation. Um, in here, I just write how to multiply complex number in the exponential form, and it's also, I mean, it works as usual, but I thought it would be nice to write this down. So you have your number and your other number. So this is the module. This is a real number, right? I mean, this belongs to the real numbers. So you just multiply your real numbers as usual, and you have one exponential and the other exponential. So when you multiply two exponential, you just add the exponent, right? I mean, there is no uh, weird or anything strange in this kind of calculation. All right, and this property here, the last one, this one is quite important and maybe more difficult to understand because, yeah, I mean, it's exactly this in the sense is you have this expression, right, where n is any integer number. I mean, you can have maybe theta. Theta can be any angle, right? I mean, maybe I should have a space. I mean, any angle, pi or pi, half pi or whatever. You have this, maybe 2 pi, right? It means that this is equal to e fine. Or if you have minus, I don't know, 50, right? 50 is 50. You can say is 2 times 45, 25. So that's basically a quite important property. And just to in the sense that you can reduce the exponent, right, in order to clearly understand this. I mean, it would be stupid to have here like, oh, see 5,040 pi, right? I mean, you can do that for sure, but why do that if you can write this just as some lesser number, right? An easy way to understand this is just because a to, I mean, this number, well, it's just one, right? I mean, for every, I mean, if n is an integer, right? This complex number is one, right? And we can go back and to our 2D plane and understand that because if you have, may you have a to the power of this one, right? It will be n equals to one, right? It means that you are, uh, what you are, where you are, okay, where erase it. Let's say you are going to be, I mean, if you have module one, you will be here, right? But then just for the sake of clarity, you are doing 2 pi, you have a 2 pi angle. It means you are doing the whole circle, right? I mean, 2 pi is the whole circle. So basically, you are at the very same point as you were before, right? I mean, and if you have module 1, as I was saying, you will have orange maybe. If you have module 1, right, at this point, you will do your ShuPy round and you will be again at ShuPy, right? So now try to do this anytime you want. I mean, if you do this 2 times, 3 times, I mean, you are just doing circles, right? And you are always going to end in the same point. And that's basically why if you add an end here, yeah, because it's going to be 2 pi, 4 pi, uh, yeah, 6 pi. No? You are just going around in circles, but when you finish every circle, you are always in the same point. So that's why basically this equals to 1, right? I hope everything fine. With all that said, I think we're done for today. Here, there are some references. Oh my God, yes, exactly 1 hour. I didn't even uh, practice this before, so this is just a reference I found in internet. You can Google it. I mean, in this reference, you will find like a lot of more what I have said that I have said. I mean, these are like full books with a lot of mathematical stuff. Maybe, yeah, some complex analysis and all the stuff. So, yep, that would be everything. If there are any question, anything you would like me to do or to answer, or if not, we can call it a day. And that's it.